Here is the HSP plant. It's very fragile. But afterwards you can come up and look at it. Very fragile. There are two daughter boards attached to it with is the video up.
I've got 20 copies of the color code on paper with the blue words showing, so that's half the people here.
So you have no dynamic ability to make them go away any longer.
In the HTML, no. But I'd like to get that.
That's the problem with our interactive environment. It's really great to use, but it's hard to show. Here is the power supply for HAPRIS. It is a lithium-ion cell with a 1.8 volt regulator attached to it and a 7.5 volt trickle charger attached to that. So this is a wall wart, and the whole thing is hokey, but maybe, depending on the future of green arrays, we'll get some little power supplies made, some little boards made, and people can buy kits and play with them. HAPRIS Creek is truly a wondrous computer. It has 360 computers you can program. 9 chips. I have only used chip 0 and chip 1. I've never managed to get any further than that. I've only actually ever programmed about 20 nodes at one time. It's fun. You've got to have the right attitude because it's a lot of computers to program. I can program maybe one a day, unless I'm just copying from somewhere else. And I'll show you some of the code. And I'll also show you HAPRIS running. This is something you can't get from the website because it's dynamic instead of static. But let me drop back a notch and talk a little bit about green arrays. Green arrays is still looking for money. This is getting kind of desperate. We are planning some reorganization that may make it easier for us to get money. We really want to get money by the end of the year, which is coming up real quick. Intellisys is being completely uncooperative. I have sued them. The suit will be settled in arbitration court in February. Depending on how that comes out will affect green arrays. It will affect me. And it's impossible to predict. Last week, I had a team of forensic accountants going over TPL's books to try to see if they improperly allocated expenses to me which were none of my concern. I claim $30 million has been pissed away that way. We'll see what the arbitrators say. We don't use venture forth at green arrays because venture forth is a property of Intellisys. Instead, we use ColorForth. I think this is a great step forward. VentureForth has gotten pretty complicated, and ColorForth has not, at least not yet. No, it needn't. ColorForth has a better syntax. And syntax is what makes your language either complex or simple. Give me just a moment to power these things up. So. Sure. F10. Kevin, this is the cable. F10 should do it. Oh, function F10. I did Alt F10. Okay. Nice timing. I have typed CLK. I'll show you the code for that in a minute. And it's going to load the clock application, and it's going to display it here. And I doubt seriously if I could display it on the screen because I'm generating a 1.8 volt sync pulse, and most monitors don't like that, but this one does. Now that said XNT, didn't it? That's cute. Dvorak is the keyboard, please. Don't read the keycaps. This probably won't run. The IDE, the Haypress Creek, a combination require 2 tries to get started. So, now one thing different between my presentation and every other presentation is I'll have to mess around with Windows. I find it really offensive, the difficulty skilled people have with scrolling through menus and tapping the right things and making it all work. Function F10. On the other hand, native color force isn't perfect. Plugged in. Oh, I fixed the ground pin, but I didn't bother plugging in Apris Creek. Please connect power before complaining.
After Chuck is done, we're all going to line up and do the canonical group photo. So keep in mind that there will be instructions. We should follow them promptly or be late for dinner.
Notice also it doesn't take very long for color force to boot. I mentioned the compression last time, I think. Did I? We're now compressing the code on a floppy. It only takes 7 cylinders. Okay. This is the first time I've ever taken Apris out of the log. That's a very promising sign. Not guaranteed. Oh, power. There is the clock. If you come up and look at it closely, and if you let a little bit of time pass so that things get warm, you can see that the digits on the left are absolutely crisp. And as you go further and further right, they become a little bit, there are funny pulses on them. Now this is a great deal worth talking about. It is set at 1435 because that's built into the code. I haven't gotten Windows to tell me what time it really is yet. So hours, minutes, seconds, and 60ths of seconds. This is all generated from the crystal oscillator, which is being driven by node 21. I ought to have a map of the nodes, and I don't. Bill's posters? Yeah, that's not quite the right one, but we want to put them up somewhere so people can admire them. I'm refreshing the screen at 60 hertz. This is actually the first display I have ever been able to refresh at 60 hertz. So I've got the full capability of motion available here. And indeed, you can't really make much sense out of the 60th of seconds. This is PST. The thing I'm working on at the moment is to display AST, apparent sidereal time. And I will get there. Pacific Standard. Pacific Standard. Except it's wrong. Mean sidereal time and apparent solar time. And sometime I'll put up Mars time. I mean, given I can do these things, it's easy to do one more. I'll show you the code for this in a minute, but I'd like to show you a different display called AD. That is the display from the IDE, showing in principle the stack at the top and the contents of memory at the bottom, except I have not initialized them. Those are default values. So there's a different set of values. And here is, I am reading the A to D. I'm reading the ground reference for A to D. And this is the value I'm getting, which is jittering a little bit. And that is the calibration which would give me temperature, except it is not calibrated correctly. And here's a histogram of the values that I'm reading. Most of the values are on this central peak. It's very narrow. It's only a couple of bits spread, except for this secondary peak that I have no idea where it comes from. I speculate it's because of the power supply, that what with the very fast and erratic demands of the chip or the board, I'm getting ripple on the power supply. It's some completely asynchronous fashion that I can't see even with a scope. But I'm going to build better diagnostics so that I can actually see a display of the time behavior of the power bus inside the chip, which as far as I know has never been done by anyone before. So that's fun. This grows and grows and grows until it runs off the top. This is still growing, you can see, so this isn't a transient. This is a cumulative effect. And there's actually a little bit of a peak out here too. The consequence of this non-Gaussian distribution is that you cannot average these data and get something meaningful. I've just got to make it go away, or else clip it severely in some complicated, unsatisfactory way. See, okay. It explodes when it goes off the end. Let me show you another one. Oh, this is clock again. I don't really want to show you clock. You've seen that. I'll show you memory. Thank you very much. Here I am reading and writing SD-RAM. John proved that it works earlier. And in my context, here's a display of the contents of SD-RAM. Now that is being refreshed at 60 hertz also. So I'm really exercising it pretty well. I started off writing 16 times the address into each of the first 64 words of SD-RAM, just so I have something to show. And indeed, all those numbers are there. This is a much smaller character set. And the flicker is proportionally larger, but still they're quite readable from a distance. There's one more display I can show. And one of the advantages over VentureForce, or at least the VentureForce I've seen, is that I just have to type one of these things, a couple characters, and it all happens. It's all been pre-scripted so that I don't have to fumble. That's particularly important for me in the lab where I have very small tolerance for fumbling. This is what I call ColorForth. It is a proto-display of the character set, the 48 character set for ColorForth, in about the same size characters as you're seeing on the main screen from the PC. Here's the red word and a bunch of green words. Oh, I'm getting there. The next thing I need to do here is put some ColorForth in SD-RAM and then display the block. And you can see how all of these capabilities I'm exhibiting, we're going to add up to something in the end. I'm about a year behind schedule. Now, the way this is...
People that all of these
Yes, I'll show you some of the code. I'm displaying it line by line. If I'm on the top line of the screen, I'm displaying the top slice of each character as I go. And indeed, the computer's working very hard maintaining this display. It is literally computing each line 60 times a second. In fact, each line is also displayed 5 times in order to make it the right density. So there's a lot of repetitious calculation going on in order to avoid having to store an image of this somewhere and then reading it back. If I say def CF, here's a block in which you can see, whoops, that's the wrong CF. There's CF. There's CLK and AD and MEM and CF. HC for Haypress Creek is the one I'm currently working on, and it can't be shown. The code for AD perhaps is the most interesting. Point to a number and it shows you that block. Here is the equivalent to the pren node in VentureForth. It's just called node in ColorForth. 119 node, the code in block 1436 will be compiled and stored as a binary image to be loaded into that block. And the same with all the others. Those are the nodes that I'm using. Nodes larger than 139, like 110, are in chip 1. The smaller numbers are in chip 0. So I can load any node on the Haypress Creek board from 0 to 9, 8, 0 to 8, and put code in it and use it. Now at the bottom, you see I've labeled a few things. Node 136 generates the red image, 137 generates the green image, and 138 generates the sync. 39 up at the top reads the A to D converter. Now I'm reading the A to D converter on chip 0. I had been doing it on chip 1, but I thought perhaps chip 0 might be less noisy. That was not the case. Reading it on node 39, whatever I read, I've got to pass through ultimately to node 137 where it's being displayed. And all these other nodes along the way are doing that. In particular, let's look at 1368, which is compiled for node 113 and also for node 115. 1368, huh? 1368. Nice big 1368, so you really know what block of code you're looking at. Not very much code. This was originally compiled for node 133. All it's doing is passing what it gets from the right port, right neighbor to the left neighbor. It starts at location 0. I set the right address into A, the left address into B. Then I have this infinite loop called pass, which fetches from A, stores to B, and goes back and waits. So this node does nothing unless it gets some input from A, whereupon it executes 2 instructions and jumps back and waits for more. So this is what we call a wire node. All it is doing is acting like a wire. You don't like to do that anymore, and you have to because it's kind of a waste. But inevitably, there will be things that have got to pass data through them. Now the next block, 1370, where am I? Is very similar. except it goes from left to right. And because of the way we've alternated or reflected the nodes, as you go across the chip from left to right, you're alternately going from left port to right port and right port to left port as you go across. That's easy to sort out. This code has been thoroughly checked. It is not one of the things I look at when I'm wondering why things aren't working. There's another one here somewhere. I can't find it. There's another way of doing this, passing back and forth, which is a little more dangerous. I thought I saw a clock here. Yeah. This is the code stored in node 132. This is driving a crystal to generate a clock. And the strategy is here. No, it's here, signal. It will pump the crystal by putting out a 0 and then a 1 and then tri-stating it. It will allow the crystal to ring, which means the next cycle it will do nothing. And then it will go back and alternately pump it, let it ring, pump it, and let it ring. Ideally, I'd like to pump it once and let it ring 10 times, or 9 times, in order to minimize the amount of power I'm using to drive it. But the number of rings determines the amplitude of the signal in some strange way I don't understand. And this works, and anything else I would have to research some more. So you start it by driving it. By driving it, I mean this is a 10 megahertz crystal. At 10 megahertz, I put out signals as best I can based on the CPU speed, just timing it. After I drive it a while and get it to ring, get it to oscillate, then I can go to pumping it. Now, when I pump it, I wait for a transition from low to high or high to low, and that prompts me to actually put out a pulse to add some energy to it. So this is a very simple fun crystal driver. It's about the simplest crystal driver I can imagine. I think it's going to be most efficient. And nobody's mentioned gray words. Has they mentioned, you ever know about gray words? This is a gray word here. It isn't bright white, it's sort of dim white. It's the location in memory at that point. So I've started at 20 hex, and I've gone to 39 hex. So there's 19 hex words in between those two markers. Then I reset at 0, and there's 16 words in this part of the code. Gray words are another kind of tagged word. When the compiler encounters a gray word, it stores the current value of its program counter into it so that it's available to be displayed later. That saved a lot of people from having to count the number of instructions between here and there. Anytime you care, you just insert a gray word. There is a way to insert a gray word. This is the keypad for the editor, but it pretty much gets used up. The easiest way, the only way I can remember to insert a gray word is to go to a gray word, copy it with the key K, move to where I want it to be, and stick it down. That works just fine. Let's look at Go back to here, and let's look at red. That's 274. And if I don't want to type, I can just go like that. Here's what you do to generate the red output signal. There are three A to Ds. Aren't there? Yes. One for red, one for green, one for blue. This is the red one. Start just initializes things. Frame is the infinite loop that generates a frame. And there's lots of these code blocks have got frames in them. Generate 37 blank lines. And then a row of digits. 49 blank lines, another row of digits, 217 blank lines, and then repeat. And you can see the word blank up there is just a for next loop with a fetch store and a fetch store. That is waiting for the clock pulse that is timing the horizontal sync to come by. The first one says start of horizontal sync. The second word says end of horizontal sync. All 136 cares about are the two fetches. Tell me when I'm getting sync. The stores are there in order to pass that data on to 137, which is the green node. So blank lines are easy. A row for 249 scan lines, we're going to wait for sync and then wait for someone, the down neighbor, to send me a character. When he does, I will display it. Character puts out 3 dots. These are 3 by 5 characters. And dot puts out the pixel onto the A to D, and pixel does some timing for it. So it's rather simple, highly repetitious. I think it's making good use of the computational ability of these nodes. A what? Yes. See if I can remember where it is. There it is. This is in node 124, and those are the characters. They're octal numbers, and that's what O comma does. Converts from octal to hex. Run is the key word here. It fetches something from the right port, stores it in the A register, which is a character. It fetches the pattern for that character and stores it back to the right port. So it's acting as a memory for node, whoever's to the right of 124, 125 maybe. 125 doesn't have enough room to store a 48 entry table. That would take all of its RAM. So it borrows RAM from its neighbor, which is a very good strategy. It's better to use a neighbor as memory than as a wire. I could go on and on, but I think I've shown you the key things that I wanted to. That there are just a little bit of code for each node, and a lot of nodes cooperating to produce a result. That's why I was reading Minsky's Society of Mind. I recalled that he had myriad agents comprising our minds. Each agent doing something very simple like grasping a cup or looking for an object. these are the same kind of things. In principle, I've got 360 agents available to program some kind of application. Each agent having very simple code that is easy to write and bug-free and runs very fast. Yet all of these guys running, and you've got gigamips of stuff. It's not all that easy, though. Let me go back to here. And this description of what code goes in what node ends by going to 272, which is here. Now, this is the interface to the IDE, really. 3PA is a path. It starts at node 33, 34, 35, and runs in a continuous string through 136, 137, 138. So that describes the path by which I am going to load nodes. Having described the path, then I use it. Say here, I select path 3, and I load node 138, which not coincidentally is the last one in the list. And I work my way back through the list, loading each one in turn. Hobo just loads it, and then eCall starts it at location E. Hob0 loads it and then starts it at location 0. And when you get to the end, everybody has started and everybody's running. I don't see any general way of doing it less explicitly. I can't start everybody at the same time. I have no path to everybody at the same time. Some things depend on other people having started first, not necessarily in this order. So some nodes will start their neighbors deliberately instead of having them started during this boot process. Now these two blocks describing the code that goes into each node and then the activity of of loading and starting the nodes are repeated for each of these various applications I've got. And they're all different. I would have thought I'd have a character set, universal character set, that everybody would draw upon. But I have 3 applications that draw characters, and they have 3 different character sets. The clock with its big characters has a different character set than the memory display, and a different character set than the colorforth display. I don't see any reason all the characters should be the same, so this is expedient in various ways. The smaller character sets fit in their parent node. The large character sets have to have an auxiliary node to store them. 10 minutes left. So one more thing I wanted to say. Colorforth.com. It's got a blog telling you the tedium of my day, a Haypress Creek blog telling you the stuff I've been telling you here, showing off various applications, or at least photographs of them. A rather neglected account of what's going on with CPL for 2 reasons. One, nothing much is going on with CPL. The wheels are grinding very, very slowly. And second, every time I publish something, I get static from the lawyers saying, gee, you really oughtn't have done that. On the other hand, they do concede that having done it, there may be some beneficial effects downstream, who knows. I've also got some poems. If you haven't read the poems, I commend them to you. And that's about it. I try to keep it entertaining, but I do run out of material. I added something just recently about the bears I saw along the side of the road They were intriguing, indeed dramatic, because coming out of the rain, there were 3 brown bushes overlapping the edge of the road, and then they turned and ran away and became bears. Quite startling.
The bears in Incline Village have been in the news. Have they been visiting Green Range?
Everyone knows there are bears there. I've never seen one in Incline Village.
Yeah, somebody shot a piece. Well, it left their house.
We've got bear-safe containers for all the trash. They're not perfect, apparently, because the bears are still there.
Those are smarter than the average bears.
I can't get into them. I don't know how the bear can.
He waits to see it change state, and then he pushes it a little bit, either up or down.
That's true, but to start it in the first place, I just used a scope and said, all right, here's 10 megahertz. Say if I have a do loop or a for loop, it will count this far and delay long enough, and very hokey. What I need to do, and this isn't a crystal actually, it's a ceramic resonator which has a bigger Q. For a crystal, I would probably have to search. I'd probably have to start a strategy and scan through the region in which I thought the frequency was until I found it. The posters. Bill recently acquired a marvelous, huge drum printer from Green Arrays, which we couldn't use. He can print things like that. On the left, you see the 144 with all its I/O pads. We have one now, some now, next week, shortly, and we'll be testing them in the new test board because the pinout is different than for the 40 or 32.
Is this stuff on your website?
Yes. greenarrays.com. And on the right is a little summary of Green Arrays and who it is and what it does. Hopefully that's going to be reorganized in the next couple weeks into a form which is more amenable to getting funding. I have received questions from people asking can I invest $25,000 in Green Arrays? And there has not been a mechanism for that. I would really like to create a mechanism because $25,000 sounds real good. Or $100 sounds real good. It is. That was our intention. The problem is the valuation of the stock. What's it worth?
That's up to you. If you do a private placement, you just decide how much you issue yourself, how much you issue other people.
Well, when we get someone that wants to invest $1 million and was willing to take 50% of the company, then the company's worth $2 million. Until that happens, it's just totally indeterminate.
And it's good for a company to be on a visibility exchange and then requires a minimum network.
That's right. Now maybe we should go out on auction and say who wants to buy for how much. But that hasn't happened yet.
$1,000 a share,
Sounds good.
and would you sell for the first year at 1,000?
The problem is having sold someone equity, it isn't money that they threw away. It's money they expect a return on, and we have no credible way of assuring them that they could get a return.
There's no assurance. You can write a business plan, project what your plans are, and anybody who believes that it's worth investing, they'll invest.
Greg?
It's really isn't time to say anything about it. But hopefully by next week, we will have an instruction for more factors, layers,
We've also got the chicken egg problem. We can't sell chips until we have production quantities of them. We can't get production quantities of them until we get enough money to make them. And we've been stuck in that loop now for months. We got to break out of it somehow.
And banks aren't interested in production.
Banks aren't interested in money at all. No, banks are holding on to their money for reasons best known to them. Bruce?
There you go. There it is.
Or know people who would be interested in a venture similar to Chuck's. We will gladly put your name and send it to
Yes.
investors, investor inquiry at Reno Race. We'll come up with an appropriate name and put it as well as.
Sorry to invest.
Okay. We have to set the structure up so that it is SEC compliant. You have to be very careful about how you solicit money and what kind of presentation is done. It's not so much that you do it properly, but if you get an investor who's angry at you, who's 60 SEC on you, you have to show that you've done everything properly along the way. So we're gladly interested in talking to you. We just have to set the proper stage and tone and have the proper documents to look correct. So
And we certainly can't offer a prospectus, or do a solicitation without a prospectus and warning you of all the terrible things that can happen.
One of the things that are on the table, though, are that you buy a valuation kit from Mr. Becker and you sign it. A public act agreement is one of those which has sort of interesting figures about our current thinking of that would be much more beneficial to have a reduced buy a valuation kit and generate just better outcomes so that we have the vehicle to be able to realize revenue from those things. Sure, there were one quarter, in one place where the actual chips now, but
Right, it's being packaged. It's being packaged in the same 1 centimeter square package, but it has different pinout.
What do you see some applications, for example, of the 144 processor chip?
144 would be great for cryptology. It's got enough nodes to do all the calculations required, or FFT, signal processing.
This could be like a cell phone that does encryption, so you could have like another person with a cell phone decrypt it and send secret messages or something like that.
Yeah?
That's already in the cell phone, we just started.
Well,
that sounds like for NSA grant.
we have applied for a couple of grants and gotten nowhere. We will continue to apply for grants. The applications for the GA4 are more interesting. We're talking to automobile battery people. And an automobile battery is very often composed of these things, 1,000 of them, 1,000 little tiny things. If we put a GA4 on each one, we can measure its voltage and temperature. We can infer its current. We can balance its charge. We can cut it out of the circuit if it goes bad. A lot of nice things you can do with a lot of GA4s.
For electric vehicles?
Or even laptops, the same problem of if these batteries misbehave, they explode. And if we're watching them, we can prevent their exploding. Right. For a robot, you put a GA4 on every stepper motor. You have 100 of them maybe.
No, this is important for solar arrays and also for.
Right.
It's also important, for high efficiency solar arrays and so forth. It's important for electric car batteries. Batteries for electric cars.
It's got two characteristics. First, they're small. If you haven't seen one, I have one. And two, they are very low power. And three, they are very cheap. It's in its little plastic bag, because otherwise it would get lost. Is that little black dot at the bottom?
Let there be one
Pass it
conversation,
around.
let it be Chuck's conversation.
So there's a lot of things you can do with GA4s. It would be even nice if we could make them wireless so they could talk to each other wirelessly. We have them talking along one wire. So you have power, ground, and communication. Daisy chain these things, put a flash to boot from at the head of the chain, and you got a very, very, very low cost system.
What's your noise-free resolution?
This can only be admired.
The A to D, I was displaying, I was getting 10 bits. I should be able to get 18 bits. And that noise is preventing me from getting from 10 to 18. If I solve it, we got 18 bits. There's a trade-off between the frequency of sampling and the resolution. And 18 bits might take some microseconds to accumulate, but you get a very accurate result. For audio, we're in a sweet spot. We can measure audio to 18 bits at 44 kilohertz. Now, Greg has passed around another version of the GA4.
I'd like to thank Chuck and all the other speakers.
Time.
Because a day without a fireside chat is like a day without sunshine.
I want to give away a computer.
Do it really fast.
I will do it real fast. I have an S100 bus, dual 8-inch floppy computer with a linear power supply in the back of my car. If anybody would like to have it and play with it, let me know. What? I don't know what boards are in, but I really don't know. I haven't opened the thing up.
Help self.
So you got to take it